Hello, I thought I'd talk today about quantum mechanics again. I just wanted to go over the four main interpretations of quantum mechanics because they imply stuff about the nature of reality, basically. And as we know, quantum mechanics is rather unintuitive, at least unintuitive based on the way people have been used to thinking about reality. So I thought I'd just go over it a bit and see what implications it has for, well, maybe future thinking about science, actually. The thing is, most people, even today, a century after it's been shown to be wrong, classical physics still informs most people's and most scientists' thinking about the nature of reality. The thing about classical physics is that it's essentially local, in the sense that when object A wants to interact with object B, it either bumps into it directly, kapow, or it sends some signal to the other which travels at or below the speed of light. It gets a message to it somehow, so pop, bing, off it goes. So it's local in that sense. There's no such thing as action at a distance. So for instance, gravity, you'd think it's acting at a distance, but Einstein was able to formulate it as the curvature of space, so that, I don't know, if the sun were to disappear, the Earth would continue to orbit for another 8 minutes until the wave from space told it that there was no sun there anymore. Right, and then it would shoot off in a straight line. So it's a local theory. Quantum mechanics is non-local, in that things can happen without a signal being sent between them and with no energy transfer. This is the example of entangled particles, like two electrons or two photons created in the same event. They shoot off in opposite directions, travel to the opposite ends of the universe. You observe one of them and it turns out to be polarized this way. Therefore you know immediately the other one is polarized the other way, no matter how far away it is. And it's not that it was like that all along. It wasn't in any particular state until the first one was observed. That's the weird thing about quantum mechanics. Unless you take one of the interpretations, which I'm going to speak about, the hidden variables theory. The other thing about classical physics is it's deterministic. If you know all the positions and velocities and energy levels and dispositions of all the particles in the universe, you could, in theory at least, calculate the future state of the universe from the beginning to the end, basically, throughout all of time. Obviously it's impractical, but in principle that's what determinism is. Things that happen are determined by previous events. So when you think something, it's determined by previous things that were going on in your brain, and so on, back to the beginning of the universe. No free will. None of that. Some say no consciousness either. Weird, but there you go. Some say that consciousness is brain states, or is the brain, and that's also a bit weird, actually. I've spoken about it somewhat in other videos. Philosophically, it actually is a bit wrong, or at least it doesn't make sense, because, just as a quick aside, if your awareness of red is a brain state, then being the same thing, they should have the same properties. But your brain state isn't red. Okay? Just a thought. Okay, the interpretations of quantum mechanics. The reason it needs to be interpreted is because it is non-local and non-deterministic. It's non-deterministic because things happen probabilistically. When you make an observation, the particle could be here or it could be there. How come? That's the question. In classical physics, there's no how come. It's just obvious because it follows a straight line from A to B and you know where it's going to be because you can calculate it by a formula. But the formulas in quantum mechanics, Schrödinger's equation and all the rest of them are probabilistic. They give you a wave function which the square of the amplitude of the wave function is the probability of finding the object at position x. Whereas in classical physics, it's going to be at position x or y, and you know exactly what the reason is. In quantum mechanics, there's no reason, it just happens. So it needs to be interpreted. What does this mean? How can a human used to sort of wandering about and gossiping under trees understand this weirdness, basically? So, first interpretation is the Copenhagen interpretation. It's often characterized as saying, basically, we don't understand it, just make the measurements and get on with it. Right. The formula gives you the right probabilities. You can do your experiments, you can get the predictions, you can check them, yep, they're right. It goes a little bit further than that, really, because it requires that the wave function collapses, reality is created, when an observation is made. So, and this is fundamental to the Copenhagen interpretation, reality doesn't exist until it's observed by something. Now, they don't define what an observer is, but we know from quantum mechanics experiments that if you, for instance, send a particle through an apparatus where it can randomly go this way or that way, the evidence is that it goes both ways if you don't observe it. You just look at the end results, the effects at the end. Or if you do observe it, it goes one way or the other. You can read about the two-slit experiment anywhere, okay? Or there's videos about it. It's weird, but it's what happens. And it's been measured a zillion times. I mean, we did the same experiments actually in A-level physics at school, in fact, with a low-intensity light bulb. It worked. So, the problem with the Copenhagen interpretation is, what is an observer? Taking the minimalistic approach, people tend to say, well, your measuring instrument is the observer. When you make a measurement, that collapses the wave function. I don't think there's any evidence that this is true, but that's like a default position, if you like, with the Copenhagen interpretation. And it's also the problem with the Copenhagen interpretation. It's a big logical problem because, as John von Neumann pointed out, the great mathematician from the early 20th century, there's been movies about him, isn't that A Beautiful Mind? I think that's him. These measuring instruments, which are supposedly taking or making the observations, these are quantum systems too. So they should obey the laws of quantum mechanics. So that means that if your electron is going through its apparatus and it's in a superposition of states, so it's effectively as if it's going both ways through the apparatus, and then a measuring instrument observes it, logically, being a quantum system, the measuring instrument will itself also go into a superposition of states. There's no reason why it shouldn't. It obeys the laws of quantum mechanics. Indeed, even the human body is a quantum system. It's made of matter and energy, although those are classical concepts. For ease of thought, it's made of matter and energy, so it obeys the laws of quantum mechanics. So when a human body makes an observation of the instruments or the electrons or whatever, it too should go into a superposition of states where all possibilities are there waiting to be made real. So, what's the only possibility? John von Neumann's interpretation of quantum mechanics is that consciousness is what's needed, and in order for it not to be also caught by being a superposition of states, it has to be non-physical, external to physical reality. That's the only thing that can collapse the wave function and make it real. In John von Neumann's interpretation of quantum mechanics, it's the same as the Copenhagen interpretation, except that the only thing that can actually make an observation is a conscious being, or consciousness. Not necessarily even a being. Who knows what consciousness is if it's external to physical reality? So this is a dualistic interpretation of reality. Dualism is frowned on by many scientists who like materialism, monism, but it's been here and there in physics for a long time. Isaac Newton was a dualist, many others. Dualism is that there are two types of things in the universe, physical things and non-physical things. That's it. Physical things are matter, energy, or in quantum mechanics terms, not even matter and energy, but events and the probabilities for those events to happen. That's what's fundamental in quantum mechanics, not matter and energy. They don't really exist, unless observed. And even then, I suppose it's questionable. So the fact that consciousness has to be outside physics for it to work is a problem with the von Neumann interpretation. It may be correct, but some people see it as a problem. Another issue with it, though, is that if consciousness has to observe things for them to be real, who was observing the early universe before any creatures or conscious beings were developed by it? Now, there's a couple of ways of looking at that. There may be beings external to the universe, or consciousness is fundamentally built into the universe and always exists in it somehow, with or without bodies. It may be that there's a God. It may be that scientists in other universes are, making universes for fun or whatever, and they're observing it, but then how did they get into existence? So it's just turtles all the way down there, isn't it? So you have an infinite regress. So can a probable observer observe something which is not real physically? Well, since consciousness isn't real, I guess it can. Or isn't physical, real in that sense. It's real, but it's not physical. Mustn't get those terms confused. Presumably it can. Right, so that's the von Neumann interpretation, and it's interesting, and it's logical, which is good. It has no real logical flaws. There are some issues, like who's observing the early universe then, but as I say, if consciousness is not physical, maybe it exists without bodies anyway. And things like near-death experiences and things of that sort suggest the same, although looking at videos of it on YouTube, it's hard to separate out genuine experiences from Christian propaganda, I have to say. Anyway, another interpretation. This is hidden variable theories. This is an attempt to save classical physics. The idea is that although quantum events look probabilistic to us, that's just because we don't know all the mechanisms of what's going on. We don't have a proper theory of what other factors are causing it to happen. It's not really random. So the idea of a hidden variable theory is that the universe is deterministic, we just don't know all the details. Now, this has a couple of problems. One, it's still non-local, but Bell's inequality, Bell's theorem, if you like, you can look it up, Allen aspect experiments and later ones indicate that there are no local hidden variables. So, while there may be hidden variables, they're not local, which means you can't save determinism with a hidden variable theory. Because determinism, as I mentioned earlier, requires forces to act locally, things to physically bump into each other, they must send a signal to each other. And Bell's inequality is, the maths is a headache, you can look it up if you want. But the idea is that quantum mechanics obeys certain rules of probability, and if there were hidden variables, the results we get from the experiments would be slightly different, basically, because there would be stuff going on. And it wouldn't be completely random, it would be pseudo-random. So there would be slight differences. So the experiments have been done. Some of the results are a little ambiguous, because the difference is only slight. But overall, the majority of physicists agree that the experiments have backed up the idea that there are no local hidden variables controlling what happens in quantum mechanics. Another problem with hidden variable theories is they're rather contrived. That is, you know the result of what's going to happen from your quantum mechanics theory. If you want to make a hidden variable theory to get the same result, you have to tinker with it and make it fit the data. It doesn't come from theory, it comes from tinkering and fudging the results, basically. Fudging your maths. Another problem is it's still non-local. It requires a quantum force or a quantum potential, which does allow things to happen at a distance instantaneously. So you're still not really getting rid of quantum mechanics. You're getting rid of some of it. And also a problem with it actually is, like with classical physics, it's deterministic. There's no free will and none of that business. And whether that's true or not, it's not a very pleasant idea. The final interpretation of quantum mechanics that I want to talk about is the many worlds interpretation. This is kind of the opposite of the hidden variable one, that instead of preserving determinism and discarding non-localism, it discards determinism. It discards non-localism. Hidden variable theory is deterministic. I'm trying to phrase this so I don't confuse myself. Whereas the many worlds interpretation isn't deterministic, it's still probabilistic, but it is a local theory. So the idea is, in the many worlds interpretation, whenever some observation is made and some thing could be here or there, the universe splits into as many as necessary to make sure that every possibility happens, and you get multiple parallel universes being created all the time. Now, it's bad enough. This theory is quite crackers in a way. It's logically sound, but it's quite crazy. So if you're sending your electron through an apparatus, and it could be here or it could be there, and when you observe you find it's there, there's another universe, in fact, where when you observed it, it was there instead. It was at the other place. So, but you can't tell, you can't detect this other universe at all. There's no way to prove this theory or disprove it as far as we know as yet. And furthermore, supposing you're observing a continuous variable, so like the position of an electron when it's in its orbital around an atom somewhere, it could be anywhere in a zillion positions, right? So when an observation is made, an infinite number of parallel universes come into existence all instantaneously, with no expenditure of energy, and yet universes contain vast amounts of energy, assuming matter and energy are real, which is classical thinking, but this is a theory which attempts to preserve classical physics, at least the local part of it. It kind of fails the test of Occam's razor, which is that things should be simple and minimalistic. If every time something is observed which necessitates a zillion particles to be in a certain configuration, a zillion universes suddenly appear and will exist forevermore, presumably, somewhere. That's not very economical. Let's put it that way. It does give you some idea of the meaning of infinity, but is that really how it works? It is, as I say, also a desperate attempt to save classical physics, at least part of it, the local part. We don't, as far as I know, there isn't an interpretation which preserves both local action and determinism together. But if there is, I would just regard it as desperation. There is a theory I've seen recently that when particles are created in an entangled state and they zoom off, and you observe one and the other one is therefore instantly determined to be in a correlated state, that actually they're connected by a wormhole through space-time and a signal is being sent. This again is a desperate attempt to save classical physics and localism and all that. And therefore is probably wrong. Apart from anything else, wormholes require massive amounts of energy to keep them open. I don't think the whole Earth is making enough energy to... all of civilization isn't making enough energy to keep a wormhole open. And particles are being created and destroyed all the time and zooming off. Some of them annihilate each other, but some zoom off to the other side of the universe. And something's got to maintain a wormhole between these two particles, potentially forevermore, and trillions and trillions of other particles and wormholes constantly. I think we might see this energy. So I would say when evaluating interpretations of quantum mechanics, my rule of thumb is if it's attempting to preserve classical physics, forget it. I think by now we ought to realise that classical physics is nonsense. It's wrong. But science is conservative. People try to hang on to as much of what worked in the past as possible and just make the minimum number of changes to get the new theory, because we have these observations which need the new theory. So inching away from classical physics is what's happening. For me, the von Neumann interpretation is the most logical. Consciousness is the observer, it's non-physical, the universe is dualistic. We must like it or lump it, but that's the way it is. What do you think? Do you agree? Do you disagree? Comments below. And I'll see you in another video at some point. I'm going through a bit of a phase psychologically. I might not make so many videos for a time. I'm not sure. I might. I don't know. I'm just thinking. I'm noticing. I'm feeling like maybe I won't, but I'll see. I'll do something probably. But just in case, I'll still be here and I'll make some. But I'm probably, I don't know, I'll see. It depends. If I don't think of something, I won't make a video. Rather than just make one about rubbish or something, you know. There's plenty to talk about, but it's whether I can talk about it. I tend to talk about what I've been thinking about during the week. And what I've been reading about and so on. So if I haven't had time, then it gets a bit difficult. We'll see. Anyway. Okay then. Bye for now.